Hey everybody, welcome back to Young Engineers of Today. Hopefully you all had a good weekend. Did you do anything interesting or fun or anything like that? Went to Whitewaters. Oh, okay, cool. Sounds pretty neato. Alright, well, as long as you guys had like a relaxing weekend, that's good. Whitewater sounds pretty fun. Um, I worked pretty much all weekend, so I'm just trying to live vicariously through you guys. Anyway, we're going to be continuing with Godot. We have at least one more lesson with it. Maybe two, and potentially three. Although that third lesson is probably going to be something like customizing or personalizing our Pong game, adding some element to it that you would like to, include, whether it be like a score or, an options menu or something. Who knows? Anyway, figure something out. Regardless, today we're going to be continuing with it, and we are going to make some more progress on the scripting side of it. We'll spend a little bit more time talking about everything and going over why we're doing what we're doing and all that. Blah 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 blah. You know, nothing new here. So I've already got Godot open, so I'm going to go ahead and open up Godot Pong. It's going to spend a minute loading assets, and we can actually kind of watch it happen in the background over here. But this is what we have so far. Remember, we've got the Pong board, and we actually got it up and running, so it will send the ball off somewhere. And remember, does anybody remember why the ball isn't changing on any given run through? Like it's always bouncing down to this corner down here. Strange. And it's fine if you don't remember. It's just well, essentially, remember that whole thing I was talking about with random numbers and how they aren't actually random. We try and give the appearance of randomness with random numbers, but there isn't really a mathematical way to get random numbers. It's just sort of it's the beauty and the issue with math. You put a number into an equation, you're going to get the same result every time. And the only way we can generate new numbers with computers is with equations. So from that perspective, it's impossible to get random numbers. we can get tables of numbers that look random by, taking the same equation and plugging the answer back into it multiple times. So that we have, like you can have a table of numbers and the first number is going to be 5 and the next one's going to be 7 and the next one's going to be 3 and the next one's going to be 9, and then maybe you'll have 4 twice, and then you'll have 5 again, and then you'll have 2, and then 10, and then 1, and then, and it looks random on the surface. However, we started out with the same number each time, we would get the same table of numbers. For this reason, we call them pseudo-random number generators. Pseudo, with a P and an S, like, which basically just means like, kind of. I mean, I'm sure you guys have heard the name pseudo, or the word pseudo before, like a pseudo-intellectual. They're not actually smart, they just act like it. Maybe not in such an insulting context. But, at any rate, I'm sure you guys have heard the term pseudo before. So in this case, it's a pseudo-random number generator, which means it gives the appearance of being it gives the appearance of giving you random numbers. However, it will always produce expected results if you use the same inputs. That is to say, you will always get the same set of answers if you use the same inputs. And that is the rub. We're getting the same input every time we start this game into that little random number generator. So for that reason, the ball is always bouncing at the same angle and going off in the same direction. Does anybody remember what that initial number is called? Like there was specifically a name for it. Yeah, a seed. Exactly. It was called a seed. And again, if you guys have ever played Minecraft before, a lot of times people will be like, oh, I really like that world. What's the seed? Well, Minecraft uses, among other things, Perlin noise generators, which are pseudo-random number generators. And that's how they can get an environment that looks varied as far as like height and biomes are concerned and things like that. But again, if you input the same initial number, if you input the same seed, you're going to get the same results on those equations and the same outputs. Thus, putting in the same seed in a world generator in Minecraft is going to give you the same world that somebody else has. Exactly the same down to the very block, provided, of course, that your CPU doesn't have some sort of weird calculation errors or different rounding, means or something like that, which is not really something you're going to run into with normal working CPUs nowadays. Back in the day, that might have been an issue, but nowadays, everything's been pretty much standardized, and if your computer has calculation errors on it, well, it's time to get a new CPU anyway. So you're gonna get the same world down to the block. Now, in order to get around this, a lot of times programmers will ensure that a different seed is fed into the program every time it starts up. But then you're just kind of kicking the problem back further, right? How do you get a random number to throw into the random number generator as a seed? Again, that's not something that's really been solved. So the way that programmers get around it is they generally input the system time from the computer. The system time on most operating systems, as I understand it, will give you the time in milliseconds since, I believe, January 1st, 1970. Strange? Yes. There's a history behind it that I don't really remember, so, it would do you guys a disservice for me to try and explain it because it would be wrong, more than likely, and then you guys would be walking around with incorrect knowledge in your head, and that's something I'm going to try and avoid. But regardless, in that case, it's not a random number, but it's going to be a different number every time you start it up. And that's good enough, because then you can fuzz that with the pseudo-random number generator, and you can pretty much guarantee that every time a user starts up their program, they're going to get different results. Now again, if you manage to somehow freeze the system time on the millisecond and you've started up a program multiple times, you would get the same results each time if they used that method of, seeding the random number generator. But really, when are you going to run into a situation like that? Not often, I don't think. I hope. Probably not. It shouldn't. Anyway. So that's kind of where everything stands as far as the random number generator is concerned, and why the ball always pops off at the same angle each time. Now, as a bit of a review, you guys remember what delta is? And why we use it in process? Okay, let's back up a bit. What's process supposed to do, basically? Like, I know we have code in here, but the process function itself has a very specific purpose in the Godot game engine. It's supposed to do something. What is it that makes the process function unique, as opposed to like the ready function or something that, like some function that we would write ourselves? It's kind of a weird question, but hopefully it made sense. Let's back up a bit further than that. How often does process run? Process runs once every CPU cycle, right? That's the whole point. Is it something that runs once every time the computer asks to run the program? Like, let me put it this way: every time the program needs to be updated by the computer, every time the CPU requests information from the program so that it updates the program, updates the simulation or whatever, process is the function that is called. Process is called once every CPU cycle on everything that has process. So that means process can be called multiple times, many times. Process can be called a jillion times. However, the more times process is called, the more that the program will slow down. So process is called once every CPU cycle. With that in mind, does that kind of jar anybody's memory as to what delta is then? Excuse me. Yeah, it counts the milliseconds. Exactly. It counts the milliseconds since the last time process has been run. So then what becomes the advantage of having something like delta in a function that is called once every CPU cycle? Well, basically, in a word, consistency. A CPU could be faster or slower than average. Certainly two different ones are going to be faster or slower than one another based on how many programs they're running at any given second, based on how how powerful one is compared to the other one based on whether or not they have multiple cores processing multiple things at a given moment. So one can have a fewer number of milliseconds between each CPU cycle than another one. If we put a set speed in and just have the ball move that speed every cycle, well, we run into issues. Faster computers, you're going to have a harder game because the ball is going to be moving faster. Slower computers, you're going to have an easier game because the ball is moving slower. So what we do is we multiply that set number, in this case ball speed, by delta. And that ensures that it will move a fraction. We say, in this case, ball speed, the 80 in ball speed becomes 80, essentially, pixels per second. So it's going to move some fraction of 80 pixels each CPU cycle based on how long it has been in a fraction of a second since the last time it ran. So now it doesn't matter. You can have a CPU that runs 1,000 cycles a second. You can have a CPU that runs a jillion cycles a second. Well, it's probably actually too fast. You can have a CPU that runs 5 cycles a second. The one running 5 cycles a second is obviously going to be really janky, but the ball is going to be moving the same speed as the one whose cycles occur 1,000 times a second. Because it's only going to move as far as it will move in that fraction of a second. So, however if a ball is moving 80 pixels a second, in 200 milliseconds it's going to move whatever a fifth of 80 is, 40. No, that doesn't make any sense. 16. It's going to move 16 pixels. If it's going 1,000 times a second, after 100 milliseconds it will have moved 8 pixels. After 1 millisecond, it won't actually have moved an entire pixel yet, but after 2 milliseconds it'll have moved a pixel, so on and so forth. It'll be so smooth that you won't be able to tell the jumping from millisecond to millisecond. But regardless, the ball will update itself and also generally correctly interpolate, so it will look smoother. But the ball will update itself appropriately based on the computer speed. So that's why we do that. What about the direction? I remember I did the diagrams last Wednesday. What does that -1 and 0 mean then? Perhaps I can jar your memory with a small diagram. Remember how long I spent drawing these in Paint? And what vectors are? Yeah, exactly, the x and y coordinates. So in this case, -1 and 0, it's going to be 0 on the y, right? And -1 on the x. And since a vector is an arrow that points, that arrow is pointing straight to the left. So -1, 0, if we're multiplying the direction vector times the ball speed and the delta, that means that the ball position is going to change by however many, based on how fast my CPU is, however many fractions of 80 directly to the left, and which is exactly what's going on the very beginning right here. It goes straight to the left before it bounces off my paddle and goes off in a random direction. The Then we also did, stuff to ensure that the ball bounces against the ceiling and the floor, or the top and the bottom of the screen. So if the y part of the ball position, if the y coordinate of the ball position is less than 0, so if it's, remember, y decreases as you go up on a computer screen. So if it's at some position above the top of the screen and the y component of the direction vector is less than 0, so if it's continuing to go up, so if it's up here and it's continuing to go up, or if the ball position, the y component of the ball position, is greater than the y component of the screen size, or greater than this line right here, and the direction is greater than 0, the y component of the direction is greater than 0, or it is continuing to go down, all we do is we just flip the y component of the direction. And just the y component, which allows us to make nice little, like 45-degree angle bounces or whatever, to ensure that it continues to go in the same direction, like whether it's left or right, it doesn't, it doesn't go back to where it was initially. So if the left, and so that's what we did in order to make sure that it doesn't fly off the top or the bottom of the screen. So now we did the scoring bit, sort of. We didn't even do the scoring bit yet. We just did the bouncing off the paddles bit. So if the left rectangle, that is to say, the rectangle which denotes the collision for the paddle, has point, and remember has point was just, they both, whatever's in here and the rectangle share a point in space. Or to put in simpler terms, they overlap or touch. If that happens at any point and the x component of the direction is less than 0, so if the left rectangle and the ball ever touch and the ball is moving in this direction, then reverse the x direction, so it's heading back in this direction, make the ball move a little bit faster, multiply the ball speed times 1.1, and then give it a random component to the y. So somewhere between straight up and straight down. And then the normalize, just make sure that you don't have any sort of weird, funky stuff going on, like the ball doesn't go in an unexpected direction. Same deal with over here. So if the right rectangle has a point with the ball position, and the x direction is greater than 0, or if it's moving to the right, then bounce it off in some random direction. Whatever. Eventually this stuff will become like second nature to you guys if you ever, decide to pursue this sort of thing. But it's really, it's a very, it's some very straightforward math involved in this, thankfully. It might not make a whole lot of sense right now, and that's okay. It doesn't really matter. It doesn't have to, It might just be the syntax, getting used to it, or the way that everything's sort of nested, like this rectangle 2 mess up here, or all of these conditionals and how they all combine. Like sometimes you can just look at it and be like, what? But, don't sweat it too much. Don't sweat it too much. So here's the deal. We've gotten the ball to bounce off of the paddles and the top and bottom of the screen. What we need to do now is we need to set it up so that the ball will, if it ever hits the left or right side of the screen, it will reset back in the middle. And that's what we're going to do here. So this one's really simple. You know how we have ball position.y is greater than 0 and direction.y is greater than 0, or ball position blah 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 blah, all this business up here. We're going to do a similar thing down here, but it's going to be even more simplified. So we're going to say if ball position dot x is less than 0, or ball position.x is greater than, what is it, screen size.x. And that's it. You notice how direction was an important component of these up here, because we wanted to make sure it was heading downwards. Down here, if the ball is off the screen on the left or right-hand side, it really don't matter what direction the ball's heading in. If the ball's over here, it shouldn't be over here. If the ball's over here, it shouldn't be over here. And besides, the ball is not going to, you know, let me zoom. We're never going to be in a position where the ball is heading this direction outside of the screen. That's just not going to be a thing that happens. The ball, if it ever reaches this line, it's always going to be going this direction. And that's just the way we've coded it so far. Likewise on the other side. Anytime the ball ever touches this wall, it's always going to be going this direction. So adding a direction component to our conditionals, well, that's just adding unnecessary coding. We don't need to check for those scenarios. Because again, the ball is never going to be off of the screen and heading towards the screen on the x component of the, of the coordinates. So because of that, our conditional for checking whether or not the ball is beyond the paddle and off the screen is a lot simpler. If the ball position, the x component of the ball position is less than 0, or over here somewhere, or the ball position, the x component of the ball position is greater than the x component of the screen size, somewhere over here, then we're going to do some stuff. Let's figure out what stuff we're going to do. Well, first we're going to reset the ball position. Ball position equals screen size times 0.5. Well, that looks a little weird, right? Well, we can tell from the fact that screen size has an x and a y component that screen size is a 2D vector, just like direction, just like ball position, all of that stuff. And with any 2D vector, let's just do this, if we multiply it times a number, you end up multiplying both things in it by that number. So the result becomes 0.5, 0.5 in this particular scenario that I've drawn out here, written out here. So that's why it might look a little strange that we're just multiplying something called screen size by 0.5. But with one equation, we have conveniently set up the ball to be dropped back into the middle of the screen. So if we were to take a look at this now, it's going to mess up. Curious. I was running into this issue before, and I'm not entirely sure how it gets fixed. Let's see. I'm going to do a little bit of debugging real quick, because that's what you do when you run into situations like this. No, whoops. No. Breakpoint. Toggle breakpoint. And we'll advance one. Will it not let us? Unfortunately, I'd love to teach you guys the ins and outs of debugging too, because it is incredibly useful. But as it stands right now, it's just simply not something we have the time for. Let me go ahead and get the ball position as well. We're going to run into this, and we're going to continue to the next breakpoint. Oops, too early. Continue to the next breakpoint. Ball position is at 0, 0. Ah, yes, because I didn't comment out that other bit. Let me just go ahead and comment this out. Okay, yeah, it is 0, 0. So basically what I'm doing here is I'm debugging. This is a thing that's built into every IDE. Well, not every IDE, but most IDEs. Part of what actually makes them an IDE, and that's short for Integrated Development Environment. But debuggers are incredibly useful because they allow you to pause the program as it's running and view the contents of variables in your memory. So here I've got screen size, which as you can see is a variable we created. I've got paddle size, which is another variable we created. I can see that we've got ball speed here, which, another variable we created. And as we can see right now in real time in the memory, the program is paused, so the memory isn't updating because there's nothing telling it to. But ball speed does have the value 80 in memory. Paddle size, as we can see, is 8 by 32, and screen size is 640 by 400, which is fine, which is exactly what we were looking for. Strangely, though, as you can see, delta, it's been basically 13 milliseconds, 133 milliseconds, excuse me, 133 milliseconds since the last time delta was called. If we were to call it again, see, it's been pretty consistently 133 milliseconds between each cycle on the CPU. Now, ball position. Go ahead and keep an eye on this down here and notice how it changes. What I'm going to do is I'm going to hit continue, which is going to run the program basically for one cycle. And everything on the program, therefore, is going to update. Positions are going to get changed. New positions are going to be calculated, all that kind of stuff. So as you can see, the ball right now is at negative 10 point, well, it's negative 10 and 2/3 and 0. If we hit update again, it's at negative 21 and 1/3. So interesting. The reason why everything is screwing up before, of course I can't pull up the game right now. Let me turn off the debugger. So what we can say with pretty much with confidence right now is the reason why that little if statement I added wasn't working is because this area right here, according to Godot, is 0, 0. Our screen size is 640 by 400. That's all well and good so far, but the moment the ball moves in this direction or in this direction at all, one of these coordinates, if not both of them, if it's moving diagonally in this direction, are going to turn, I did that backwards. They're going to turn negative. They're going to be less than 0. And remember, if we go back down over here, if the ball position.x is less than 0, the ball position.y is less than 0, then do a thing. So what's going on here is as soon as the program is starting, it spawns here just like normal. It moves 1 pixel to the left, and then this if statement catches and executes. And then it moves it to screen size divided by 0.5, which then becomes 320 by 200. And then it spawns somewhere over here and starts moving in this direction. And then the cycle begins anew because there's nothing there stopping it. So this is one of the weird things that can happen with viewports and stuff like that. Now comes the question, how do we fix that? So let me see if you guys are running into this issue as well. If you were to insert this code that I'm placing into the chat box into your process function, does the game still operate as normal when you run it? Or do wonky things happen? And let me know if wonky things happen. I guess show of hands if everything's operating normally. Alright, how about show of hands if everything's acting weird? Okay, I got one hand up for weird. Two hands up for weird. Alright, well that makes 3 people, which is large enough sample size. So this is more than likely attributed to the disparity between essentially, as we said before, or as I was saying before, what it counts as 00 versus the actual, size of the screen. So what we have here in this is screen size get viewport rectangle size. Now the viewport rectangle size is going to be 640 by 400. However, we never actually asked for the position. So if, right, I have the debugger on. F9, there we go. So what we asked for was the size of this window. which is all well and good. However, we didn't actually ask it for the position of this window, which is looking more like something like this, strangely enough. Why it's doing that, I'll have to spend a little bit more time researching. I can actually get some of that done right now. See if we can't actually get this fixed before the end of class. So I believe there was an update to this since the last time I ran the tutorial, which changed some of the ways that the world space is basically interpreted in Godot. I wonder if we can get around it in a quicker way too. Let's see here. So, I made some changes to the code so far, just some temporary fixes, and from what I can tell, it's not exactly a 1/2 ratio. Like it's not offset by exactly 1/2 on the x and y, which means that the actual viewport we're looking at is different from the grid that the world uses. However, we do have it respawning in the same location, of course, showing that the ball position's at 0. Putting the ball position back at 0 means that it does spawn right back in the center of our view screen, which is good progress so far. So what we're going to do here is we are going to what's the word I'm looking for? We're going to debug this a little bit more. So that's the position of the ball. We'll run to the next. As you can see, it is now almost to the paddle. It'll hit the paddle and start heading in the other direction. Or it will go past the paddle. That's unusual. That shouldn't be happening either. It probably totally skip past the paddle check because of the debugging, which is the thing that shouldn't happen, but Sometimes strange things happen. So now the ball position is negative 64 and 0. What I would love to do is actually get the position of the ball when it's on the edge of the screen, so we can get some idea of where exactly the edge of the screen is according to Godot. This is what debugging is good for. Debugging can be kind of tedious, I will admit. However, it's actually a very useful way. Aha! Negative 42. Weird. It's a very useful way to get a feeling for what's going on behind the scenes in your game. So let's do this. If ball position.x is less than negative 42, oops, let's turn off debug. I will also, I didn't actually implement any code yet in order to, but see, as soon as it's hitting over here, it is responding, which is more or less exactly what we want. Notice how it's moving in the same direction each time. That's because we haven't coded anything in yet in order to change the direction of the ball whenever it's respond. That's fine. I just wanted to make sure that it was responding in the proper location. That works out fine. That is the only problem with the debugger. Okay. Let's change the ball speed to 10. We'll restart it. I know this must be terribly exciting for you guys to watch. This is sort of the process of debugging things. It's not a terribly interesting process to watch, but it's actually pretty interesting to do once you get the hang of it, because it's, again, getting a sort of a look at the under the hood of your game, as well as kind of giving you clues for the puzzle that is coding, and getting used to all the foibles that sort of can sometimes plague you when you are coding. So curiously, our screen size is actually not listed correctly. If we put 32 in here and run it and get rid of our breakpoint so we stop running into that issue again, here we can see our ball bouncing off. Well, that also needs to be fixed. And then respawn. And then the paddle's in a weird position over there. It's also not accurately giving us the top of the screen either. Let's say this is about 40 then. Double the speed of it. Say it's about 39. Well, let's say it's 32. Negative 32 to 32. Let's take an educated guess that it's exactly 100 units across. And it is. It's exactly 100 units across in length. So this brings up an interesting new problem. No, 64, excuse me, 64. I can do math. It's exactly 64 units across in length, which is 1/10 of our original given size. So now, when this actually, so there we go, we should see it bounce off the top of the screen. No, it doesn't. It's 1/20th. No, it is 1/10. I'm doing math wrong. I'm bad at math, everybody. It's kind of disturbing for a computer programmer to be bad at math. But here we are. Okay, so that's a little bit smaller. So that's a little bit too small. Also, the paddles are way too large, the actual rectangles for them. This is kind of neat to see it play itself, though. As it gradually speeds up to the point where it becomes entirely unplayable. And then it gets stuck in a loop. Oh well. 25 to 25. So it looks like it's about 30 to 30. It might be 32 to 32. It might be actually stretching the same coordinates. Let's see here. Just about. Looks like it's 32 to 32. Negative 32 to 32. So that's going to be an issue that I'm going to ponder over the next couple of days and figure out why exactly it's doing that, because that's curious. That's curious. Regardless, it shouldn't be a perfect square that is stretched in order to fit a rectangular screen. That's not normal. Because that's what essentially is happening to the grid here. Our grid of coordinates is, let's just say for the sake of argument that it's 5 by 5. So 5 by 5, which is fine on a square screen. However, we're looking at a rectangular screen, which means that 5 vertically is normal, but 5 horizontally, everything is way stretched out so that you have the same number of coordinates there. So that brings up an interesting little issue, which I will spend the next couple of days researching, and we'll have an answer for on Wednesday, hopefully. Anyway, it's 7:57. I'm not going to keep you guys here any longer than you guys, need to be here, or want to be here. So I'll go ahead and do the poll questions, and then we will break for the next couple of days, and we'll see you again on Wednesday.